Hello, everyone. Okay, so if this works, then I'm going to tell you about my recent paper on bounds on light sterile neutrinos, where we combine constraints from laboratory measurements and cosmology. And you can read all about it now on the arXiv, or you can listen in the next 20 minutes or so. Okay, then let me jump right in. So why are neutrinos interesting? If we're looking for new physics, well, neutrinos are always good for surprises. So we know now that neutrinos have a small mass. And to give neutrinos mass, you actually need physics beyond the standard model. The fact that neutrinos have mass also means that the flavor states and the mass states are different, and we observe oscillations between the flavor states. Neutrinos are only weakly interacting, so that makes measuring them very, very challenging. And we have to combine as many ways to measure them as we can. And cosmology is one particularly nice way of actually learning something about neutrinos. So let me very briefly tell you about neutrino oscillations. So the fact that neutrinos have mass, as I said before, means that the flavor basis and the mass basis of neutrinos are different. And to convert from one to the other, we need neutrino mixing matrix. So what that means in practice is if you have a source where you emit neutrinos of a given flavor and you let them propagate for a while, then during the propagation, the time evolution will be determined by the mass eigenstates. And the detector will measure a different flavor mix. And the flavor that you measure at the detector then depends on the distance traveled. All right, and in a bit more detail, this transition probability is governed here by, as I said before, this mixing matrix U. It's governed by the mass splitting between the states and an additional L over E factor, which basically just gives you the distance traveled in units of energy. And you can see this as, in this example plot that I drew here, where we start with an electron neutrino, we let it propagate. So the scale here is a couple of thousand kilometers, actually. So the electron neutrino will slowly convert into tau and muon flavors, and depending where your detector sits, you will measure a different superposition of these flavor states. All right, so now we want to look actually for sterile neutrinos, or for additional neutrino states. And in this oscillation framework, any extension is pretty straightforward. So you can just make the mixing matrix bigger and include additional neutrino states. One thing you have to keep in mind here is that any additional neutrino state is either has to be very heavy, or it's sterile in the sense that it doesn't take part in the weak interaction, because we have very precise measurements of the Z decay where any other neutrino state would have shown up by now. So that's why we're interested in additional sterile neutrinos. All right, so we can still find them in oscillations. So if we have a source and a detector and we let the neutrino oscillate and propagate, then the additional state will reveal itself via its effect on the oscillation probabilities. And if you set up your experiment in such a way that you're measuring at quite small L over E's, so short baselines, then the other oscillations don't have really time to develop, and you're only focusing on the additional effect that the fourth sterile state would have. Okay, and that simplifies the problem, of course. So there are two different general setups. You can either measure the appearance of a given flavor. That means that you create, for example, muon neutrinos, and you actually measure electron neutrinos that were converted from these muon neutrinos. The big advantage here is that the background can be very, very small. The problem is that the signal usually is also very small. And in terms of steriles, what you're measuring with these experiments is a combination of the mixing with these two flavors, the one that you create at the source and the one that you detect. You can also measure the disappearance of neutrinos. So that's usually done where you have a source of a given flux. And at a given distance, or at a varying distance or varying energy, you measure how this flux is modulated. And again, the modulation of this flux then depends on the mixing with this additional fourth state. All right, and one famous experiment that actually measured this was performed at LSND and later repeated in a very similar setup by the MiniBooNE collaboration. So what they did was they looked at muon neutrinos that were created out of a muon accelerated beam, and they measured the conversion into electron neutrinos at varying distances. And what they find is an excess of neutrinos. So there are more electron neutrinos measured than they expected, and more electron neutrino measured than would be explained by only the oscillations using the states that we know of. So one interpretation of these results is then that there is an additional state and which modulates the flavor oscillations at short distances, and the corresponding mass scale is in the EV range. So MiniBooNE data combined with LSND points towards an EV scale sterile state that actually boosts the electron neutrino production or conversion. There are other anomalies in the neutrino oscillation sector measured at nuclear reactors. So there are various disappearance experiments where they measure the electron neutrino flux that comes from nuclear reactors at varying distances or energies. And what many of these experiments find is a modulation of the flux with L/E. So one of the results is shown here on the left. This is by the Dance experiment, where they see more or less clear modulation of the electron neutrino flux. And the same is seen by various reactor experiments. And if you combine all of this reactor data, it also points towards an EV scale sterile state that modulates these electron neutrino flux probabilities. The combined significance of these measurements is something like 3 sigma. That's shown here on the right. This is the preferred region where you can actually explain the observed signal. And yeah, it points again towards this EV mass scale. Now, if you combine both of these measurements, LSND, MiniBooNE, and the reactors, you would also expect to see something in the muon neutrino disappearance channel, but this doesn't appear in measurements done by IceCube or by MINOS. And that's very, very confusing, actually. Okay, so there's right now no model that can explain all of the experimental oscillation data that we have. And yeah, people are still arguing what is going on here. So there are several papers on global fits, and brief summary is that there's no global fit with acceptable goodness of fit. So there's no model out there right now that can explain all of the results at once. Nevertheless, we want to check these signs towards EV scale sterile neutrinos. How else can we check this? We can, for example, look at beta decay measurements. So these measurements try to resolve the endpoint of the tritium decay spectrum, and any additional sterile state or any additional neutrino state would contribute to the suppression. So it would contribute to this effective M beta mass that is actually measured by these experiments. And the current limit by the Catherine collaboration lies at something like 1.1 electron volts. You can also look at double beta decay. So if neutrinos are Majorana particles, that means if they are their own antiparticles, then you can observe this process shown here, where two neutrons decay into two protons without emitting any neutrinos. This is a very rare process, if it's possible at all, and the half-life of this process is proportional to this m beta beta mass scale, which is again just a coherent sum of all of the neutrino states. And if there's an additional sterile, then, or an additional fourth state, it contributes to this m beta beta mass and modifies the half-life. So if you put all of these together, the current limits on the half-life are something like 10 to the 26 years, which translates to a limit on m beta beta of the order of 0.3 electron volts, depending on how you combine your experiments. All right. So if we look at the preferred region from the reactor anomaly, then what do the other measurements tell us? So if we look at neutrinoless double beta decay, then unfortunately there are no interesting bounds on this region. And also from the beta decay measurements by Katrin, they're only in very mild tension with these reactor anomaly results, but they can't rule them out. So now the question is, of course, can we go to cosmology and actually look for a signal of such neutrinos? And in principle, of course, we can. The big challenge is that we have to get from the fundamental sterile parameters, the mass splitting and the mixing matrix, to cosmological observables, such as the CMB power spectrum or the matter power spectrum that we can calculate by our Boltzmann codes. The sterile neutrino is produced in the early universe, and its production is governed by a Liouville equation, which gives us the density matrix of all of the neutrino flavors or all of the states. And this looks very scary because it actually is. So we have the effect of expansion, we have vacuum oscillations, we have interactions with the lepton background, we have interactions with the neutrino background, and we have weak interactions scattering between leptons and neutrinos. And all of these processes are important at different times and are important to accurately model the abundance of a sterile neutrino in the early universe. To make this feasible computationally, usually people assumed just a 1+1 setting where you have one active neutrino coupled to only one sterile. And in the results that I'm presenting here, for the first time, we went to a full 3+1 setting where we model all the three active active neutrinos that we know of, coupled fully with all their mixing matrix elements to the sterile neutrino. And this is possible with this fortepiano code, which is quite new. And if we look at the evolution of the distribution function of the sterile calculated by fortepiano, shown here, then we can see basically over time how the sterile is populated. So early times are high temperatures, shown here in red, and later times are shown in blue and low temperatures. And you can see as over time, the sterile state is populated until it reaches an asymptotic value where the oscillations effectively stop when the densities are of the wrong order of magnitude to actually boost the oscillations into the sterile state. And the resulting distribution functions actually is very well described by something like the Dodelson-Widrow model. So if you know the contribution of the sterile to an effective, and if you know its abundance, then you can, to a very, very high accuracy, model the full cosmological perturbations. Okay, and how does this look like if we scan the parameter space of mixing matrix elements and the mass splitting? So for this plot that I show here, I kept all of the mixing matrix elements to all of the different neutrino flavors equal. And you can see that the sterile is a relativistic particle either if the mixing is very large or if the mass scale is very small. And of course, that makes a lot of sense. We can also look at abundance corresponding to this plot above. And here the sterile abundance is shown as a fraction of the dark matter density. And we can see that for most of this parameter space shown here, the sterile is only a very, very small part of the total dark matter density. So if you want a sterile neutrino to be the main dark matter component or the only one, then you have to go to much larger mass scales of at least keV or so. And that's outside the scope of this paper. Okay, and the density of the sterile grows with an effective, or it grows with the mass scale. All right, so how does the whole setup then look like? We start with mass splittings and mixing matrix elements. We use Fortepiano to calculate the sterile distribution functions. With these distribution functions, we can directly compute the cosmological perturbations. In practice, this is a bit time consuming, so we take a shortcut and just extract the contribution to n effective and the density of the sterile from the distribution function and use those as a shortcut to calculate the cosmological observables. And the main constraints then come from combined CMB and BEO data. And they set a limit on the maximum additional contribution to n effective and to the neutrino mass. And this is how we rule out the sterile parameter space part for part. All right, so if we run this whole machinery, what comes out is this. Okay, so here are the results, the constraints from CMB and BEO data on the sterile neutrino parameters. And one thing you can see is that the constraints on all of the different mixing matrix elements are of the same order of magnitude. They look very similar. And we can also see that they are ruled out as soon as any of the mixing matrix elements is larger than 10 to the minus 3 or so. And the reason is that as soon as any angle is larger than this, you start really creating a large contribution to n effective, and that's ruled out by the CMB data. There's a degeneracy with the mass scale, and you can easily understand it by looking at this plot that I've shown before. Basically, you can always wander along this diagonal. There's a certain maximum n effective that's allowed by the CMB, and you can reach the same n effective either by increasing the mass splitting or by increasing the strength of the mixing. All right, and if we now go back to our reactor anomaly and at the other oscillation limits, then what does cosmology say about this? Well, it convincingly rules the sterile neutrino at EV scale out. Okay, so any neutrino that would be able to explain this reactor anomaly would lead to a fully thermalized fourth state in the early universe, and that would have been seen by now. All right, we can also look at the MiniBooNE results. So this is in the MiniBooNE parameter plane, the cosmological limits, and we're still running the full analysis with MiniBooNE data at the moment, but I did my own little analysis with pen and paper here and copied the results from the plot on their paper. And luckily, we are many orders of magnitude off. Okay, so again, cosmology rules out the sterile neutrino explanation of the MiniBooNE data. So whatever is causing these anomalies, it's at least not a simple sterile neutrino, because that would have been seen by now in cosmological data. We can also now transform the cosmological limits into the parameter space that's probed by beta decay or neutrinoless double beta decay experiments. And we can see that cosmology can set very tight limits on these parameters also directly. The disadvantage, of course, is that those cosmological limits are model dependent. So if you actually change your cosmological analysis and include, for example, a dark energy or varying dark energy component, those limits will slightly change, but not by much. Okay, so in the same way as the normal neutrino constraints are relatively robust in these changes, the same is true for the constraints in sterile neutrinos. All right, we also explored effects of different priors on the results. And there are there are several reasonable assumptions that you can make for the prior for such an analysis. So you can either assume a logarithmic prior on the mass splitting, you can just set a prior on the mass splitting itself, or on the mass scale of the sterile. And all of those are reasonable choices, if you ask me. What you're doing then is basically you're setting more weight towards higher or lower masses or mass splittings. And as we've seen before, in the constraints, there's a trade-off between the mass splitting and the mixing matrix element. So with the prior, basically, you can also set more weight at one end of this diagonal. But overall, the big picture is unaffected. So the crucial point here is that in this parameter region, where the reactor anomaly lies, any neutrino would be fully thermalized and is ruled out. It doesn't matter which prior you assume for that. We also went into detail and tried to understand where the difference between our full 3+1 setting with 3 active neutrinos and previous studies is. And at first glance, the results are very different. So I'm showing here the 1 and 2 sigma constraint contours. 1+1 shows the analysis done only with 1 active neutrino. 3+1 shows our full analysis that we presented before. And they differ. But the main difference between them actually is only a parameter volume effect. So if you have 3 active neutrinos, there are just many more ways in your parameter space that you can have large mixing angles with one of the active neutrinos. And as soon as you have large mixing with one of them, you thermalize. And then you're ruled out. So once you account for this difference in parameter space, or in this, you account for this volume effect, the limits look essentially the same. So this is an important message if you want to test sterile neutrino cosmology in the future. You don't have to go through the full pain and solve the Liouville equation for 3 coupled neutrinos. As long as you take this into account, you're fine. All right, so let me conclude. The situation in these short baseline oscillation experiments and in reactors at the moment is very unclear. So as I said before, there's no model that can explain all the data right now, and we are not able to find a good global fit to all of the data sets. In such a situation, it's very important to have different data sets, so you can have cross-checks between them, and any at least simple sterile neutrino explanation for either reactor or short baseline anomalies are convincingly ruled out by cosmology. So any of those sterile neutrinos would have been seen by now by Planck. And cosmology is also able to provide the strongest currently available limits on beta decay parameters. And if you want to read more about this, either ask me in the next days or check out our paper. And thanks for listening. I hope this worked well, and talk to you soon.